right, let's continue. So over the break, I just looked up a few things here. The average income in the United States for a person, okay, one person. Any ideas? What does the average American bring home a year? Annual salary? 38,000? No idea? 59,000. Now I don't know. I just looked it up real quick on Google, so I don't know how accurate that is, but that's your average American's income. All right. So that might be. I don't know if that was household. Hold on.
Does that count like all the rich too?
Yes, it does. This is household income. So that's both, I mean, if you have two people in the household, you know, I don't know what, how many households are two incomes or not, but that's your average household income, all right? Now, when it comes, I'm leading up to something here. You've all heard of the stock market, right? Stock market is where you put money into companies. You say, hey, I'm going to hope that their value grows. Then you basically own part of a company, and then you can sell that part of the company later for either more money or less money, depending on if the value of the company has gone up or down. So in the stock market, you can expect annually to have somewhere between 12% to 15% growth, right, for your investment. Now, you can lose your money also, okay? And you can be very conservative about the way you invest, or you can be very aggressive. I'm just trying to get some numbers up here for us, all right? So, here comes the problem. Let's say you win that lottery we were talking about the other day, okay? Let's say you win the lotto, or maybe you inherit some money, who knows? You somehow, you find yourself with, let's just go with $1 million. Okay, let's just somehow you've stumbled upon $1 million. Of course, you could go out and buy all the things you want, but let's say that we invest that in the stock market, all right? And let's go with a very conservative number. Let's say that we get a return of 6.5%. Well, let's just see what happens after 1 year. Okay, so you invest at 6.5% for 1 year. So that means you're just going to keep doing what you're doing, working your job. You're going to put that money into the stock market, all of it, and see how much you have after 1 year. All right? Let's say interest is compounded continuously. How much will you have? After a year. Yeah, well, I already said a year, all right? So what formula am I using? The second one, right? The shampoo formula? What is P? $1 million. E, what is our interest rate?
6.5.
Okay, so we convert that to a decimal. 0.065, right? Be careful with that because you're moving the decimal point 2 places to the left. And then time is 1. time is 1 year. So let's take 1 million and let's multiply that times E raised to the 0.065. When I do that, I get 1.067159.024. So I did this first. I did E to this power first. Then after I did that, I'm going to multiply it times 1 million. I get 1067, 159.024. Well, what does that mean? How much have you made? You've actually made $67,159.02 or 3 cents by just sitting on your money and letting it grow for you in the stock market. You've made more than the average American household brings in a year by just sitting on the money, right? Wow. So here's something that's kind of crazy the way this works. Let's say this was $10 million. Say you hit the lottery, you didn't get the big one, the $480 million one. You hit the $20 million one, and then taxes, they take out half of it anyway, so you get 10 million take home, right? And you go put that in the bank. All that would happen here is a decimal point would move over one place to the right, which would mean you would make how much a year? 671,000. Right? Is that not insane or what? So like, you hear about these people who hit these lotteries and then 3 years later they're broke. And a lot of that's because instead of investing the money and living off of the interest, they just go spend the money. So if you go and you win $1 million and go buy a $500,000 home, that $500,000 is now gone. You can't earn off that money anymore, right? It's gone. So this is pretty depressing. You think about people who are extremely wealthy, the top 1%, they say the top 1% of the population has 90% of the wealth or something like that in the country. You think about people who are like billionaires, right? Imagine if you have $1 billion. So take this, put 9 zeros after that. It's people who are worth $1 billion. That means you have to move this decimal point over, right? We need to add 3 more zeros to that. So add 3 more zeros to this. So if $1 billion invested conservatively in the stock market, that's millions of dollars, right? Move this decimal point over 3 places. Right, so 1, 2, 3. A billionaire is going to make $67 million a year off of their money. It's nuts, right? Okay. Y'all seem thrilled. So go win the lotto, okay? And then go invest your money conservatively. All right, let's talk about the next topic. Let me look at the review real quick, make sure I've talked about what I want to talk about here. The review for the final. Yeah, okay. So I think I'll start the next topic with a question, all right? You plan to invest, let's just go with $2,000 into an account at an interest rate of, let's say, 3.5%. So maybe this is like a CD. A CD is where you basically give your money to the bank and you just promise them you're not going to come back and ask for it for a certain number of years. So you say, here's my money, I'll be back in 5 years to get it. Or I'll be back in 10 years to get it. And that's called a certificate of deposit. If you do that, then you can get a little bit higher rates of return on that. So let's say you plan to invest $2,000 into an account at 3.5%. Here's the question. How long would it take to double your money? And interest is compounded continuously. Okay, so I'm just putting that there at the end. The type of interest we're working with here is the one that's compounded continuously. All right, so this problem is a little different than the last one, all right? Let's talk about what the difference is. Which formula are we using? Shampoo one, right? Okay. What do we know here? What do we know? Do we know P?
Yes.
P is what? 2,000. Do we know the interest rate? 3.5%, we know that. Do we know the time? We actually don't know the time, right? That's actually what we're interested in, is knowing how long we need to leave it there. Do we know how much we want in the account at the end?
Yes, double that.
Double it, 4,000. So our equation actually looks like this. 4,000, that's doubling our money, must be equal to 2,000, right? E to the 0.035 t, right? And we are trying to determine what this t needs to be, right? What does that t need to be in order to double our money? So look at this. This is an equation, right? But this is an equation that you've never had to deal with ever. Well, I mean, unless you've done this sort of stuff before, okay? But we have not dealt with this. I mean, we can solve equations. Like I could ask you this equation right now and expect that you could answer that, right? This is a linear equation. You could solve that for x. I could give you this equation. I could give you that, right? I could ask you to solve that. You'd use a quadratic formula for that, wouldn't you? Move everything to one side, use quadratic formula. You can solve these equations. But notice that the thing you're solving for, x, is always down on the bottom, right? It's never up in an exponent. Here, the thing we're trying to solve for, kind of like the x, is up in the exponent, right? And right now, we do not have a way of solving problems where our variable is up in the exponent. We need to figure out if there's a way to do this. And that's what the next topic is about, all right? So right now, to answer this, we won't be able to, all right? I'm just trying to give you, kind of a lead into why we're going to do the next section, all right? All right, this is where the wheels start to come off. This is where the plane starts to wobble around a little bit in the air. We're going to talk about logarithmic functions. All right, now we could spend 3 weeks talking about logarithmic functions. All I'm going to do is just give you the very, very minimum of what you need to be able to solve this equation, all right? We want to be able to somehow use this concept to answer this question, all right? So I'm just a very, very sneak peek preview, not really full treatment of logarithmic functions. So here's the basic idea. Let's say I take this function, let's look at the function 2 to the x. What type of function is that? That's an exponential function, right? That's what we just got finished talking about? I'm going to draw like a visual representation of what this function does. This is our input, this is our output. If I plug the number 0 into that function, what does it spit out? If I plug 0 in here, what does it spit out? 1, right? If I plug 1 in here, what does it spit out? 2, right? I'll keep this color coordinated, 2. If I plug 3 in here, let's say, what does it spit out? 8, right? All right, so that's what the function 2 to the x does. It takes these numbers and sends them over here, right? Is there a function that would send these numbers back to where they came from? So I'll give you a slightly different example so you can see what I'm talking about. Let's take the function f of x is 2x. Not 2 raised to the x, 2 times x. Then what does 0 get sent to? 2 times 0 is 0, right? Where does 1 get sent? 1 goes to 2. Where does 3 go? 3 goes to 6. Is there a function that would take 0 back to 0, 2 back to 1, and 6 back to 3? The function that would basically undo this function. So this function doubled everything, right? So the function that took you back would have to do what? It would have to divide by 2, wouldn't it? It would have to take half. So the function that would take you back from 6 back to 3, 2 back to 1, and 0 back to 0 would be a new function. I'm going to call it g of x, which is half of x. Right? So if this is the function that takes you from the left to the right, this purple function right here, half of that would take you back. Do you agree? Plug 0 in here. What's half of 0? 0, so 0 goes back to 0. How about 2? What's half of 2? 1, so 2 goes back to 1. If you plug 6 in here, half of 6 is 3. It goes back, right? Okay, so this function can be undone using this function, right? My question here is, if we have 2 raised to the x takes us from here to here, what function takes us backwards, right? Is there a function that takes us back? And unfortunately, there is not one that you can come up with like this, like where it's just half of it. We actually have to just call it something, and that's where we get the term logarithmic functions. So we need a function that goes back, takes this back, takes that back, right? That function, I'm going to tell you what it is right now, is this. We write log, a subscript 2, and then x. That is the function that takes you backwards. Okay, so I want to make sure you understand that. So I'm going to erase all this side right here, and I'm going to ask you to see if you get this or not. Where should this function take 1? Back to 0. Where does it take 2? To 1. Where does it take 8? Back to 3. So let's write that down. If I ask you what log, I write log, and then this right here we call the base. Log base 2 of 1. You're telling me the answer is what? 0. What is log base 2 of 2? 1. And then what is log base 2 of 8? 3. So the log base 2 function takes 8 back to 3. Log base 2 takes 2 back to 1. Log base 2 takes 1 back to 0. All right? Now, another way you can check to see that you've done this correctly is using this thing where you just make this little loop. What would happen if I said 2 raised to that power? What's 2 raised to the 0? 1, right? What's 2 raised to the 1? 2, right? What's 2 raised to the 3? 8, right? You see how that little loop works? So let me ask you this. What's log base 2 of 16? So 2 raised to what power would give you 16? So 2, 4 of them, right? So this would be 4. So this takes 16 back to 4. Does that kind of make sense? Okay, so at the end of the day, here's what I want you to know about log functions. Log functions undo exponential functions, all right? That's what they do. They undo them. So in general, given an exponential function, a to the x, right? This is an exponential function. Then the function g of x equals log base a of x undoes f. And this is called the log base a function. So if someone gives you an exponential function like 2 to the x, then log base 2 of x will undo it. It'll take everything back to where it came from, all right? So I'd like us to talk about some of the properties of these logs. Remember, I told you when I started this, my goal is to just get us to a point where we can solve that equation, right? So I'm just trying to go shortest, easiest path to get there. So I'm going to now need to ask you to discuss or to consider some of the properties of these logs, these logarithmic functions. So maybe you can help me. What would log base a of 1 be? If I don't tell you what the base is, can you tell me where it's going to send 1 back to? Not to A. Good guess. 0, right? Because remember, when we plug 0, I erased it. Remember, when we plug 0 into any exponential function, a to the 0 always gives us 1, right? So if I ask you to send that 1 back to where it came from, it has to go back to 0. So for any logarithmic function, this will be 0. Agreed? Regardless of the base. If you try and send 1 back, it's got to go back to 0. And you can check it if you don't believe it. Just check it. Does a to the 0 equal 1? Yes, right? A to the 0 equals 1. Okay, let me ask you this one. What is log base a of a? That's the one that's 1. Yes, this is going to be 1. And the reason why is because a raised to the first power should be a, right? You all still with me? Okay, here's another property of logs. What is log base a of a raised to the n? This is the big one. This is the big property we need. To be able to solve equations, this is the one we need. Well, it's going to lead us to the one we need. What should this be equal to? So try and do this. A raised to the something has to be equal to a raised to the n. So here I said a raised to this number, a raised to the 1 must be equal to a. A raised to the 0 must be 1. A raised to what power is equal to a raised to the n power? N. This is n. Right? It's n. Check it. A raised to the n is a raised to the n. So it'll take a to the n back to n. Okay. All right. I'm going to leave those up. Hold on, let me think of how I'm going to do this. Okay, I think I know how. How about this? Log base A of x squared. No, you know what? Let me do this. Let me change that squared to n. All right. So my first question is, can I use this formula? In this formula, this base and this base are the same, aren't they? It's a and a here, so this loop works, right? And that's just n. But here it's a and here it's x, right? So I cannot do the same thing. Do you all understand that? Okay. I'm going to write down the property of this one. I'm going to tell you what this is equal to, and then we're going to talk about it. Okay, right there. And I'm going to put a huge star next to this because this is the big daddy right here. This is the one we need the most. So let's try and understand where this property comes from, all right? I'm going to try and explain it to you. Okay. Log base a of x times x times x times x times x, we have n of these. Okay, x to the n means this, right? That means x times itself n times. Agreed? Okay, so then this turns into log base a of x plus log base a of x plus log base a of x, and there are n of these. So I'm telling you that to get from here to here is another property. I'm not trying to convince you that this is true. I'm telling you that this is a property of logs. All right, so it's like I've given you these properties. This is another property of logs, that if you have multiplication inside of a log, you can switch it into the sum or addition of a bunch of separate logs. So that is a property. If you believe this, because you have to believe it, because I'm telling you it's a property, all right? If you believe this, how many of these logs will I have? How many of those logs are there? There's n of them, right? And if there's n of them, then this is the same as saying that I have n of these logs. I have n of those. It's kind of like if you wrote 4 plus 4 plus 4, that's the same as writing that I have 3 times 4, right? If I have 3 4s added, that's 3 times 4. If I have n logs added, that's the same as having n times the log. That's this property right here. X to the n splits up. Using this property, we get addition, and then when you add them, we get this. Now, the main thing I want you to see from this that I've starred here is really what's happening in this property. If you ever see log with any base of something to a power, what really happens to that power in the next step? It drops out in front, okay? It drops out in front, all right? You okay with that? Okay, star that, we'll come back to it. I know this seems weird. Once we use it, you'll be like, okay, I think you'll feel better about it. I hope. So where do I want to go from here? We got that property. Okay, let's talk about special logs. 2 special log functions. What do you think they are? We had 2 special exponential functions, right? What do you think the 2 special logs are? What bases? 10 and e, right? So we have this one, log base 10 of x, right? That's your base 10 log. And then you have another log that's log base e of x. These are very special logs. This is the log function that undoes 10 raised to the x. This is the log function that undoes e raised to the x, right? Those are the 2 special logs. Now, this is where I think things just kind of have fallen apart when it comes to the history of mathematics. We never write this log this way. If we ever want to use that log, the way we write it is we just write log. We don't put the subscript 10. It's kind of like this. When I write this, everyone understands that I mean the square root of 4. This really technically should be written this way. Because if I do this, that's something different, isn't it? So if I put that there, that's the cube root of 8, that's 2. But if I don't put it out here, everyone understands it's a 2, right? Same thing here. If you write log, it's understood that it's a base 10, okay? So if you write log x, everyone understands it's a base 10. On your calculators, you should have a key. Where is it? Right under the green key, second key down on the left side. Do you see it, log? That's your log base 10 key. Just to show you how that works, can anyone tell me what this answer should be? Don't use your calculator. What should that answer be? It should be 1 because this is really log base 10 of 10. That's really what that means, right? So this is saying 10 raised to what power gives you 10. So your answer should be 1. So on your calculator, if you do log 10, hit enter, you're going to get 1. Okay, so this is the special notation for that special log. And then this one has its own special notation. We write ln, that's an L and that's an N, and then x. And this is called the natural log. That's the one we're going to be most interested in right there. The natural log of x. Okay. One more property. One more property, and we will be ready to solve the equation. Last property is called the change of base formula. And it goes like this. If you have any log with any base of anything, then this is always equal to the natural log of x divided by the natural log of a. We will use this one also. And I want you to see this one in action. Right? I want you to actually see this one work. So here's an example. If we say, what's log base 5 of 3? Think about what this is asking you. This is saying 5 raised to what power is 3, right? And nobody in here is going to be able to tell me what that is. 5 raised to what power is 3? Agreed? Okay, but this formula tells us that if we have log base 5 of 3, we can use our calculators and just take the natural log of, what would this be? This would be the natural log of 3 over the natural log of 5. So on your calculator, find your natural log key, which is the third key down on the left. And I want you to actually do that. Natural log of 3, and then divide that by natural log of 5. And somebody give me an answer. .682, right? 683, somewhere around there. Approximately 0.683. So what this is saying to us is that if we raise 5 to this power, we should get something, we should get 3. 5 raised to that should give us 3. Okay. If you feel like you don't know what's going on here, it's okay. Don't worry about it. Just let's go back to that example, okay? I'm ready to go solve that problem. We're just going to use, I put a couple of toolboxes in, or a couple of tools in your toolbox here. We're just going to use them now, right? So the problem we had stopped on was we were trying to double our money. And we were right here, 0.035, if I'm not mistaken, t. Is that where we were? Okay, that's where we are, and we're trying to solve for t, right? Yes? Okay. First thing I'm going to do is divide both sides by 2,000. Do y'all agree I can do that? Okay, divide both sides by 2,000. What is the left side? 4,000 divided by 2,000 is 2, right? Equals e to the 0.035 t. With me? Yes?
Yeah, no.
That's okay? That's all right? Paris? No? You sure? Okay. That's just division, so we should all be good there. Now, here comes the critical step. I'm going to try and find a way of taking this entire expression and dropping it out front. I want to be able to drop it out front so it's no longer in the exponent. But the only way I can drop things out front is if there's a natural or a log in front of it. Because we had that property I told you to write down that went like this. Right? This basically said if you have any log, doesn't matter what the log is, and you have something to a power, you can pull the power out front. That's a property of logs. I'm about to use that. The problem is I don't have a log. Do y'all see there's no logs here? So I'm going to introduce logs on both sides of the equation. This is very similar to like adding a number to both sides or multiplying both sides. I'm going to take the log on the left side. Now I can use any log I want. Any log. Okay? Because that property works for any logs. So the log I'm going to use is the one I have a key for on my calculator, which is the natural log. I could also use the log, log base 10, but the natural log's the one we normally use. So I'm going to do the natural log of 2 on the left side. On the right side, I'm going to do the natural log of e to the 0.035 t. You all understand what I did there? Taking natural log on both sides. Okay, on the left side, I'm going to leave it alone. And on the right side, I'm now going to bring this property into play. This is like the n, right? That's like the n. And that now will drop out in front of the log. So I will have 0.035, but what's still there? Time, oh, t, yeah, I forgot to put the t. T, but then still after that, times, I have natural log of e, right? Natural log of e. Now let's see if anyone can type that into their calculator right here. Just this piece. You know what? Let's not. Let's see if we can get that answer without even doing any calculation on our calculator. Doesn't this really mean log base? What's the base of this log? The natural log. What's its base? E, right? That's the base. And then I'm plugging in E. Elizabeth, what is that?
1.
1, good. It's 1. This is 1, isn't it? Because this is saying E to what power gives you E? Right? E, no, that would give you 1, right?
Oh, yeah.
E to the 1 gives you E. So this is 1. And it will always be 1. Every time you ever do a problem like this, if you ever see natural log of E by itself, after you drop this out, it has to be after you drop that out, that is going to become a 1 every single time. And that's a great thing, because now look at the equation you have. Look at this equation. Natural log of 2 is just a number you can do on your calculator, isn't it? And then a number times t. So you can solve for t here, can't you? So on our calculators, let's do natural log of 2. When you do that, the left side becomes 0.693. I'll just stop there, equals 0.035 t. What's our final step? Divide both sides by 0.035. And you get 1.98 equals t. Okay, so what does that tell you? What does that tell you?
That's how much time it takes.
That's how much time it's going to take to double your money in that investment, which means 2 years. So if you start out with $2,000, you put it into an investment where you're going to get a return of 3.5%. Are y'all getting a different number?
I got 19.
Oh, you got 9. Oh, did I leave a decimal out? Oh,
You got 19.
oh, that sucks. I was going to say that seems way too short. What did I point? Oh, I did .0693. Oops, 19.8. Yeah, thank you. That sucks then, doesn't it? That's a lot longer. At 3.5%, it's going to take you almost 20 years to double your money. Not a good investment, probably, because with inflation, $2,000 today versus $4,000 20 years from now, they're probably worth the same thing, right? Okay. I think we're going to have to do some more of this when we come into class on Monday. And then I have a few other topics that are still related to this that I'll cover. And then we'll have the test on the following class. So we're going to talk a little bit about carbon dating. You should be able to do every problem on this review right now except for number 15 and number 17. There's only 2 that you shouldn't be able to do. You got that? 15 and 17? So go ahead and take the weekend to look through this. You'll find that this review is very similar to the tests that you've taken. I've just kind of consolidated the problems that I think are important for you to look at. So make sure you go home, try this out, and then I give you 2. Make sure that you come Monday with questions, all right? There you go.